Hi everyone. Today we're going to be looking at section 10.2, lines tangent to a circle. So when we see that word tangent, if we have a line that's tangent to a circle, that means it's a line in the plane of a circle, so it's sitting on the same flat surface, that intersects the circle in exactly one point. So you'll notice that this line is just barely skimming that circle, and it meets at a point called the point of tangency. Okay, so it's where they intersect. Now, our first theorem for today says that if a line is tangent to a circle, then the line is perpendicular to the radius drawn to that point of tangency. So I'm going to grab a straight edge, and we're going to draw a radius that meets at the point of tangency. Now, our theorem tells us that this radius is always going to be perpendicular, so notice that it makes a right angle with the tangent line. Okay, so we're going to be using that a lot in this section. A lot of times you're going to see right triangles and a number of other things that we've worked with in the past. Now, the converse is also true. So if you have a radius that's perpendicular to a line, and if that line just touches one point, that means that the line must be a tangent. Okay, so looking at example number 1, it says here that ED, the segment here, is tangent to circle 0. Now you'll notice that there's a radius that goes from circle O, the center, to point D. So I know that those are going to make a right angle. Now we're asked to find the value of x. So if you look at this as a large triangle over here, we know that the sum of the three angles in a triangle have to add up to 180. So if I add these three angles, they add up to 180. So using my calculator and subtracting, we get x is equal to 52 degrees. Okay, now moving on to the next problem. We have two radii drawn to these 2 points. Now we're told that both of these segments are tangent to the circle. So that tells us that both of these angles are right angles. Okay, now we need to find the value of x. Now there's a characteristic that we learned about earlier. A quadrilateral that's 4 sides, right? Sum of the angles is equal to 360. So in this particular case, I'm going to have 117 plus 90 plus another 90 plus x, and that sum is equal to 360. Okay, so again, doing a little bit of subtraction here. Subtracting each of those values from 360, I get x is equal to 63. Okay. Now our last problem on this page says, is KJ, this line out here, is it tangent to circle P at point J? We need to determine if there is a right angle. Now you'll notice that it is a triangle in this picture. Now in a previous chapter, we said that you can determine if you have a right triangle by using Pythagorean theorem. So what we're looking for here is we're trying to see if 6 squared plus 9 squared, that's these two sides. Is that going to be equal to, we'll put a question mark, the hypotenuse, which would be 10 squared. Okay, now doing a little bit of addition here, we've got 36 plus 81. And adding these together, we get 117, and that is not equal to 100, which tells us that the answer is no. We do not have a right triangle, therefore, we don't have a right angle, okay? And if we don't have a right angle, that means we don't have a tangent. All right, let's go ahead and flip to the next page. And we have another situation where we see this triangle, and in this case, segment ST is tangent. So I'm gonna go ahead and mark the right angle. Now we wanna use Pythagorean theorem again to solve for that missing piece. Now Pythagorean theorem says we're gonna do x squared plus 24 squared. Those are both the legs. Now, careful with the hypotenuse. This whole thing is the hypotenuse, which is x plus 18. We're adding those two segments together. So we're gonna have x plus 18 squared. So at this point, we have quite a bit of algebra that we need to simplify. Now I'm gonna use my calculator to simplify 24 squared. That's 576. So I have x squared plus 576 is equal to. Now we have to be careful on the right-hand side. Squaring a quantity means to multiply it by itself. So actually, we need to FOIL in this problem. So I'm gonna draw my FOIL markings. So we're left with x squared is the first, 18x is the outside, 18x is the inside, 18 times 18 is 324. Okay. Now you'll notice that there's an x squared on both sides. If I try to combine these like terms, what ends up happening is that they cancel, which is kind of nice. And we're left with 576 equals 36x plus 324. And at this point, we can just solve for x. And we get x equals 7. So the radius of our circle is 7. Okay. So let's try one more. So in this diagram, we're trying to determine if is line PM tangent to circle N at this point. Okay, so we're trying to see if we have a tangent line. And later, in the next part, we're told that LK is tangent to the circle and we need to find X. Okay, now one of the things I'm going to give you a hint on for this part is that if the radius is 9 over here, that means the radius is 9 over here. Okay, now this isn't an easy problem, but I do want you guys to give it a try. At the very least, you guys should get part A and then give part B a try. I'm going to pause the video here for you guys to attempt this problem. Okay, so here are these solutions. In part A, the line is not tangent because if this were a 90-degree angle, you'll notice that the sum of the angles is not equal to 180. Okay, so that's not going to work. For the second part, we're again using Pythagorean theorem because we know that a squared, which is 9 squared, plus b squared, which is this quantity here, is equal to the hypotenuse, which is this whole segment, x minus 1 plus 9 squared. Now, this part can actually be simplified. If I combine my like terms, I get x plus 8 quantity squared. And then we would continue the problem just like how we did in example 4, okay, where we FOIL, cancel out our x squareds because they're the same on each side, and combine like terms. So we should end up with x equals 7, okay? Now, our next section is talking about finding the lengths of segments that are tangent to a circle. Now, we're told that these two lines are tangent. You'll notice that we have the right angles drawn. Now, we want to figure out if there's a relationship between xz and yz. So I'm going to take a look at this picture and say, okay, well, I know that my radii are going to be congruent to each other. If I were to draw the line drawn to z, you'll notice that it's the same for both triangles. We've got a triangle on top and a triangle on bottom. And you'll notice that the triangles are congruent by HL. So we have a right triangle, hypotenuse, leg, hypotenuse, leg. So that tells me that by CPCTC, those two segments are congruent, okay? Now that is gonna lead us to a theorem that we're gonna see on the next page, but for now, let's just finish this problem. So if TX is equal to 12, well, so must this one be. If TZ is equal to 20, how can we find the perimeter of this entire figure? Well, I know that I have a right triangle, so I'm going to use Pythagorean theorem. 12 squared plus, we'll call this b squared, is equal to 20 squared. So using Pythagorean theorem, we're going to isolate b. Take a square root. And we get 16. So in order for us to find the perimeter, we just add up all those sides. And we should have a perimeter of 56 units. Now, the fact that these two segments were congruent to each other leads us to our next theorem. That says, if two segments with a common endpoint, notice that common endpoint A, exterior to a circle, are tangent to the circle. So you'll notice the right angles, that tells us we're tangent. Then the segments are congruent. Okay, that is always going to be the case. Now, sometimes you guys will have circles that are drawn inside a figure. We've probably seen these words before, but we'll just reiterate. So a circle is inscribed in a polygon. Sometimes I like to think of that as inside. When each side of the polygon is tangent to the circle, okay? Similarly, a polygon is circumscribed about the circle when each side of the polygon is tangent to the circle. So we would say that the circle is inscribed in the triangle. We'll say inscribed in the triangle. And the triangle is circumscribed about the circle. Sometimes you see that word around, but if it's circumscribed, it's on the outside. If it's inscribed, it's on the inside. So if we look at example number 6, it says that circle O is inscribed in triangle ABC. Find the perimeter. Now we call this a walk-around problem, and you'll see why in a second. So let's start by looking at this side of my picture. So you'll notice that point B, our segment is tangent to the circle at each of these points. If I cover the rest of this up, I know that these two segments have to be congruent because they meet at that common point. So I know that this side is 15. Now, if I cover up, let's say, this part of my picture, notice that FC and EC meet at a common point, and they're both tangent to the circle. So these are both going to be 8. And finally, where are we at here? If I have 10 up top, I have 10 over here. So in order for us to find the perimeter now, we're just going to add up all these sides. So I have 2 times 10, 2 times 15, and 2 times 8. You could just add them all up. You'll get the same answer. So we should have a grand total of 66 centimeters. And now the last problem is another walk around. I'm gonna have you guys give this a try. The worked out solutions will get posted in the scanned notes on Google Classroom. So that concludes section 10.2. Hope you guys enjoyed it. If you have any questions, come to my office hours either Wednesday or Thursday from 10 to 11. Thanks, have a great day.